Andy, you just let me know and I should start.
Yeah, do you want to turn on your?
Wait a minute or two. Yeah.
Maybe just 1 minute, but do you want to turn on your screen share again?
Yeah, I'll do that. Okay, I'm good to go.
All right. Well, as the final speaker of our conference, we're delighted to have Greg Moore, who will tell us about summing over bordisms in TQFT.
Well, thank you, Andy, and the other organizers for inviting me to participate. I'm really sorry I wasn't able to come up to Yale. New Haven is just so beautiful at this time of year, and I always love visiting Yale and the math department at Yale. So happy birthday, Sasha. I've been giving a lot of birthday talks, and you know, it's often hard to find good photographs of the birthday person at a blackboard. And but you're easy. There are lots of great photographs of you enthusiastically explaining things at a blackboard. It's really wonderful. So I couldn't even choose which one I liked best. So I first, for those others on the call, I think I first met Sasha on the early afternoon of October 24th, 2008. I can date it that precisely because I had come up to the third New England string meeting at Brown University to give a talk about a paper I had written a few months earlier with Davide Gaiato and Andy Knightsky. It was about a construction of hyperkähler metrics. And already at that time, Andy was starting to explain to us about all this really cool work by Fock and Goncharov, which somehow was somehow, which we didn't understand really that well at the time, but we realized that somehow this work of Fock and Goncharov was relevant. Andy brought these papers to our attention, and we were just starting to learn about that. And so after the talks were over at the meeting, I had dinner with Andy and Sasha and a fourth person. I can't remember who it was. Maybe Andy remembers or Sasha remembers, but it was just a wonderful meeting. It was one of those great dinners where you exchange all sorts of ideas, and you know, there's just math, you know, going all over the place, you know, explaining to people and writing lots of equations on pads. And you know, after that dinner, I was very excited. I wrote down some notes about all the things that Sasha wrote, and I went back to my notes, which I still have. And you know, I took little snippets from those notes, which with 2020 hindsight, I can see now were things that Sasha was explaining to us that became later very, very important to our work about cluster transformations, cluster varieties, the different kinds. I like this one where he mentions conformal blocks of Liouville theory. And of course, the Teichmuller modular group and the, you know, the groupoid associated with that, and A infinity categories and their relations to BPS degeneracies. So that was a really wonderful dinner. And I've had many great discussions with Sasha ever since then. Now, today I'm not going to talk about four-dimensional n equals 2 supersymmetric Yang-Mills. I'm going to talk about something quite different. You know, Sasha, you must be tired after all these talks. You know, a whole week of talks, and Andy, I mean, you guys have had to listen to all these talks. So, so I'm going to talk about something. You know, this is really easy stuff, and so I'm giving you a break. it's the last talk of the conference. After some of the things that I've been listening to, this is really going to be very, very easy for you. So let me get into it. Here's the outline for the talk, but don't be alarmed. The sections aren't separately very long. So what's the motivation here? So the motivation is a long-standing problem in quantum gravity. Now, I don't know what quantum gravity is any more than you do, but vaguely, it's something like assigning probability amplitudes to some kind of sum as in a path integral over metrics on some space-time y, maybe weighted by the Einstein-Hilbert action or some variation thereof. And the longstanding problem in quantum gravity is if we sum over metrics, should we also sum over topologies? So that's been around for as long as people have realized that maybe something like quantum gravity should exist. It's a little sharper in one of the best models of quantum gravity, the ADS-CFT correspondence, because in that correspondence, very roughly speaking, you have at least in Euclidean signature, you have a hyperbolic manifold Y, and it has a boundary, and you want to say that the quantum gravity on Y is somehow equivalent to some kind of field theory on the boundary. And in most of the models that people usually talk about, the boundary has one component. So, you have a quantum field theory on that boundary, and it's somehow dual or equivalent to the quantum gravity on Y. But it's easy to have hyperbolic manifolds where there are multiple boundary components. So which quantum field theory is going to be dual to the bulk, as they call it, the Y? And if none of them is, then how do you combine the different quantum field theories? So it's not at all clear. And this puzzling aspect of the ADS-CFT correspondence, sometimes called the factorization problem, really goes back to the very beginning of the subject. It was remarked on by Yao and Witten, late 90s, and made a little sharper by Maldacena and Mayos, who wrote actual supergravity solutions with hyperbolic. It involved hyperbolic three manifolds with multiple boundary components. Not a big deal from the mathematical point of view. And it was this issue became even sharper after some work by Saad, Schenker, and Stanford, where they identified the sum over topologies in a version of two-dimensional quantum gravity known as JT gravity. They showed that if you sum over topologies in JT gravity, as you really must, you get a matrix model very closely related to the work of Mariam Marzcani. So there were very beautiful results. It was clear that the correct thing to do is to sum over topologies, but it raised very pressing conceptual questions about whether string theory should be dual to an ensemble of quantum field theories, and what kind of sense can we make of that, and what would the ensemble be? And it raises a whole host of questions. So motivated by these issues and some other developments in quantum gravity, Don Maroff and Henry Maxfield considered it a curious topological model of 2D gravity. And an essential part of their discussion involved summing over topologies with disconnected components. And so, I looked at that and I said, gosh, that's something I ought to be able to understand because it's just topological field theory in some sense in two dimensions. I thought I knew everything about topological field theory in two dimensions. Now, the Maroff-Maxfield paper is definitely not written in a way that's very accessible to mathematicians. So I told my graduate student, Anindya Banerjee, well, why don't we try and understand this in terms of standard topological quantum field theory and see what these guys are doing from a mathematical perspective. And I will comment a little bit on the Maroff-Maxfield paper as we go through, but not as much as I ordinarily would, because I'm primarily addressing mathematicians in this talk. Okay, well, I'm sure this is not necessary for the present audience, but just to set notation on topological quantum field theory, let's review that quickly. So first, what is a bordism? So let X in and X out be smooth, compact manifolds of dimension d-1, then by definition, the bordism Y from X in to X out is, first of all, a d-dimensional manifold Y, together with some disjoint decomposition of its boundary into, we call it dy in and dy out. Dy in and dy out need not be connected manifolds themselves. It's just some partitioning of the boundary components into in and out. And we have to have diffeomorphisms of dy in with X in and dy out with X out, and embeddings of collars of X in and X out into Y, which reduce to the specified diffeos on the boundary of Y. So that's the full glorious definition of a bordism. So for example, if I have 3 points as X in and 5 points as X out, that's a bordism, an unoriented bordism. There are 105 pictures that look like this, but there are infinitely many bordisms from 3 points to 5 points because, of course, I could always include disjoint unions with circles. So now the bordisms are morphisms in a category, a bordism category. And for the purposes of this talk, a topological quantum field theory is just a monoidal functor, Z, to the category of vector spaces over a field kappa. So that means that if I have a d-1 dimensional closed manifold, X, then Z of X is going to be a vector space that's physically to be thought of as the vector space of, quote, states associated to a spatial manifold, X. And the monoidal structure, the monoidal functor, means that if I take the disjoint union of spaces, I get the tensor products of the space of states. And if I have a bordism from X in to X out, then the functor associates to Y a linear transformation, sometimes called the amplitude, from the initial state space to the final state space, in such a way that if I compose bordisms, I get the composition of linear transformations. Notice that in my convention here, I'm composing subsequent linear transformations on the right, okay, which is contrary to what people usually do. They usually compose on the left, but I'm going to do it on the right. It's just more convenient for a lot of formulas. All right, so that's topological quantum field theory. Are there any questions? I can't see the audience here, so okay. So let me define what I call summed and total amplitudes. So as I just observed, you can have different bordisms between fixed X in and X out. So now supposing we're given a topological quantum field theory Z, which I'll call the seed TQFT, we could define the summed amplitude to be A, to be the sum over all of the bordisms Y between the fixed X in and X out. And we sum over the Z of Ys, but we weight the Z of Ys by 1 over the order of the automorphism group of the homeomorphism type of the bordism, restricting to the identity on the boundary. So when I gave a version of this talk in February, Maxim Kontsevich was in the audience and he immediately started objecting here. He said, well, I don't think this is the right way to weight by the automorphisms of Y. And he may well be right. I'm going to do it this way because this is what's universally done in the published literature. But I'm sure Maxim has an interesting point. And I had some interesting discussion with him. Yes, Kevin, you have a question.
Maybe I'm going to say the same thing Maxime said. If you're doing, topological strings, you would use an integral over the moduli of integral over some model of b diff y, and it would be a more elaborate story. But you don't want to do that?
Well, I'm doing the simplest thing. As I said, at the very end of my talk, I was going to say, gosh, we ought to generalize some of what I'm doing to topological strings. And then I totally agree with you. So yes. Well, all I could say is I agree, but I'm going to be doing something much simpler in this talk. As I said, my goal was to just understand what Maroff and Maxfield was doing and maybe generalize it a little bit. But I agree with you.
And also, I mean, O of Y is normally a huge infinite-dimensional group, so you mean its components?
Pardon?
And the automorphisms of Y is normally some big infinite-dimensional group.
I can't quite catch it. What it's going to be doing is it's going to be very trivial for us, and you'll see that in examples. So it's basically just going to be dividing by the orders of symmetric groups, acting on components that look the same.
Okay.
But which restrict to the identity on the boundary. So as I said, that's what people are doing in the literature, and our goal was to understand what people were doing in the literature. And I'm very, very open. I'm very receptive to other ideas for dealing with automorphisms of Y, for reasons you'll see. But anyway, I wanted to put that caveat out there right at the very beginning here. But so this is what we're going to do, because this is what everybody does. So each of the Z of Y's is a linear transformation from the ingoing state space to the outgoing state space. Okay, so if we add up over all the Y's, we get some linear transformation, which I call the summed amplitude. Okay, and that immediately raises some questions. Well, does that sum exist? If it does, is it computable? Now, this is kind of an open-ended question, but if you could compute it, does it have any interesting properties? And if so far I've only defined a TQFT at what's called the top 2 levels, but what about extending to the fully local TQFT? Okay, so here's some answers. Well, it only seems to exist, at least in the most naive sense, in 1 and 2 dimensions. And I'll explain what goes wrong in D equals 3, at least in the most naive sense. In 1 and 2 dimensions, at least in all the examples that I've examined, it does exist. And as I said, what properties does it have? Well, that's an open-ended question, but this talk is going to be stressing one particular property, which I call the splitting property. That's going to be the main theme of this talk. And since we can only go up to 2 dimensions, the extension to the fully local TQFT is still something of a question. And the answer is yes, it does extend, in the sense that it extends to the open and closed TQFT. Okay, so now it's very useful to think about what I call the total amplitude. So we're going to consider simultaneously all the amplitudes from all possible ingoing spatial manifolds to all possible outgoing spatial manifolds. So what kind of mathematical object is that? Well, we should take the sum over the direct sum of the state spaces over all the smooth connected D-1 manifolds considered up to diffeomorphisms. That's a countable sum. So we have the sum over X of Z of X. I'm going to take the tensor algebra of that. So that basically accounts for all possible in or outgoing spatial manifolds. And then our total amplitude is just going to put together all the different summed amplitudes into one big linear transformation, which I call the total amplitude. Now, because we're summing over the bordisms, the amplitude actually descends to a linear transformation on the symmetric algebra of the sum over X of Z of X. I'll call that the Fock space of the seed TQFT. Okay, so that will be an important object throughout the talk. And so our main object is to understand this A bar linear transformation on the Fock space of the seed TQFT. So now we come to the splitting property. So for the simplest thing we could do, if we take the ground field to be the complex numbers, then the statement is that we could put an inner product structure on the Fock space of Z such that there exists an inner product space W, which I'll call the splitting space, such that there exists a linear transformation from the Fock space of Z to W, such that this total amplitude is of the form phi dagger. Microsoft will not let me put in a phi dagger without a lot of extra trouble. So I'm calling it phi star, but I would have preferred to write phi dagger. Anyway, now here I want to remind you that I'm thinking of the homomorphisms or the linear transformations from V1 to V2 is V1 dual tensor V2. So it's very natural to compose linear transformations on the right. So phi star, phi dagger is a linear transformation from Fock space of Z to Fock space of Z. Okay, let me make a few comments about this. First of all, this A bar need not be positive definite. So the existence of such a formula is not completely trivial. At the very end of the talk, I'll talk about how my worry is that maybe I'm telling you something totally trivial. I'll explain why. But even if the existence is trivial, certainly finding the explicit W's and phi's in examples seems to be slightly non-trivial. Another remark is that the splitting space is certainly not unique. If I have one splitting space, I can take a direct sum of copies of the splitting space. And if I have one phi, I can choose a bunch of positive numbers, p alpha, which sum to 1, and then replace phi by the sum over alpha of square root of p alpha times phi alpha. It might be that there's a minimal splitting space in the following sense. There might be a splitting space Wm and splitting maps phi, such that if I have any other splitting like this, I can find a map from Wm into W, so the standard kind of universal property. I haven't really seriously thought about whether such a minimal splitting exists or not. Maybe the mathematicians here can tell me that it has to exist based on some abstract nonsense. Anyway, that's an interesting possibility, but I don't know about that. Okay, let me show you some examples of what I'm talking about. So let's begin with one-dimensional TQFT and unoriented one-dimensional TQFT. So then Z, the functor, is completely determined by just a finite dimensional vector space, which is the value on a point, together with a symmetric non-degenerate bilinear form B associated with this bordism from 2 copies of V, 2 points to the empty set. And then in this case, the Fock space of the seed TQFT is literally the Fock space of the, or the symmetric algebra on the vector space V. And I'm going to be really sloppy, apologies to the mathematicians, I'm going to be really sloppy about questions about completions of the Fock space. And so I guess, strictly speaking, the symmetric algebra would just be polynomials. Sometimes we're going to see some infinite sums. So now let's start computing the total amplitude. So let's start with the simplest thing where we have the in and out spatial manifolds as the empty set. So we have just bordisms of nothing to nothing. So the connected bordism is the circle. Z of the circle is the dimension of the vector space. Now here you see the automorphisms coming in. So the general bordism is just a disjoint union of n circles. The automorphism group is just the symmetric group, permuting them. So if we divide by that 1 over n factorial, then we have an exponentiation, and that's the total amplitude. Now here, it's useful to introduce the notion of a Hartle-Hawking vector and a Hartle-Hawking covector. So the original idea of Hartle and Hawking is that the wave function of our universe is somehow the sum over all bordisms from nothing to us, or to something in general. So mathematically, we can give that some substance by considering the following. We could take the ground field, and that certainly embeds into the Fock space as the 0th component of the symmetric algebra. And then we have our total amplitude on the Fock space. And so the image of 1 in the ground field is some vector in the Fock space, and that I will call the Hartle-Hawking vector. And then there's a covector, which is the sum of anything goes to nothing. So we take the total amplitude from the Fock space of Z to the Fock space of Z, and then we project it to the ground field. And so that defines an element of the dual space of the Fock space, which I'll call the Hartle-Hawking covector. Okay, so now let's calculate the Hartle-Hawking covector in this one-dimensional case. And to make things as simple as possible, let's take our vector space to be one-dimensional. Ground field is C. So now we can choose a vector V whose norm squared is 1. And here it is. Here's the Hartle-Hawking covector. And it's not hard to see why this is the right thing, because you have to, it's an unoriented bordism from a bunch of points to nothing. Well, you have to have an even number of points, like 4. And how are you going to make bordisms to nothing? We have to connect up the points in pairs. So there, in the case of 4, there are 3 pairs. And you should all be thinking, oh gosh, this is just Wick's theorem. I'm just contracting points in pairs. And yes, in Wick's theorem, the number of ways of contracting 2n points is indeed 2n factorial over n factorial 2 to the n. Good. So now we can go from the Hartle-Hawking covector, aside from its conceptual importance. It's also very computationally useful because you can go from here to the general amplitude. How do you do that? Well, you just apply the U-shaped bordism to take ingoing points to outgoing points. So in formulas, there's a non-degenerate bilinear form, which means there are canonical isomorphisms between V and V dual. And so you apply that to this Hartle-Hawking covector, and you immediately get this as the total amplitude. So it's not a big deal. So this is the sum in the symmetric algebra V dual. The sum lives in the symmetric algebra V dual times the symmetric algebra V, which is, of course, just the linear transformations on the Fock space of V. Okay, so now let's see the splitting formula. So now let's indeed remember Wick's theorem, which, among other elements of Wick's theorem, it observes that there's this combinatorial factor as just the value of this Gaussian integral over the real numbers. So that motivates us to introduce a vector psi n in L2 of R, and L2 of R is going to be our splitting space in this example. And so an easy calculation then is that the overlap of these psi n and psi m is odd, is 0 if n plus m is odd, and is our combinatorial factor if it's even. And there's a mistake here. It should be n plus m factorial divided by n plus m over 2 factorial, 2 to the n plus m over 2. So I made a mistake in that equation. Anyway, here's the splitting map. So it's a sum of V dual to the n tensor psi n. So you imagine taking the adjoint and then contracting the size, and then you get just that the desired combinatorial factor to produce this kind of formula here. Okay, so that verifies the splitting. This generalizes, of course, to higher dimensional vector spaces. And one nice way in the general case of packaging all the information is to look at the Hartle-Hawking covector on the exponentiated diagonal. So you think of a vector V in the vector space V, then e to the little v, some element in the Fock space. If we evaluate our Hartle-Hawking covector on that, in the general case, we get this formula. So that summarizes. And then as I explained, first of all, the Hartle-Hawking covector is multilinear and totally symmetric. So it's completely determined by its values on the diagonal. And then by using this dualization map, you get the total amplitude. So that's the whole story there. The results can be extended to oriented one-dimensional theory. In this case, Z is determined solely by a single vector space, so that Z on a positively oriented point is V and Z on a negatively oriented point is V dual. And then it turns out that, at least in one form of writing the splitting formula, that W, this is not obvious, but W turns out to be L2 of the torus. So let's go on to 2 dimensions, unless there are questions. I hope you're following. This is supposed to be really easy stuff. I mean, it's just very simple topological field theory. Okay, so now if we look at 2 dimensions, let's look at 2-dimensional oriented TQFT. That comes in many flavors, and our results, well, we have results, complete results in some cases and partial results in others. So if I look at totally closed and semi-simple TQFTs, then the answer is yes, we have total results, complete results, open, closed, yes. For the non-semi-simple closed case, we only check this in examples, and in the open closed non-semi-simple case, well, we didn't even really try to think about it. Okay, so let's talk first about the 2-dimensional closed semi-simple TQFTs. So as everybody knows, going back to the early 90s or before, thanks to Friedan and Dijkgraaf and Siegel and others, the TQFT is completely determined by the value of the functor on a single circle, which is a finite dimensional commutative Frobenius algebra. And the Frobenius structure is given by taking the disk, thinking about the disk as a bordism from the circle to the empty set. And that defines the trace map on my Frobenius algebra. And we have the property that if we multiply and integrate or multiply and take the trace, we get a symmetric non-degenerate form. And I'll talk about the data for the open-closed case later. Okay, so in the case where this Frobenius algebra is semi-simple, that means we can write it as a finite sum of one-dimensional Frobenius algebras, which are generated by idempotents. So X, capital curly X, is a finite set of points. The idempotents obey this nice equation here, and all the data in the Frobenius algebra is given by the trace on the idempotents. I'll call those theta sub X. And so they're invertible elements in the ground field. And so Graham and I propose that really one should think of this as two-dimensional topological string theory, where the target space is the spectrum of C. It's just a finite set of points. And of all the infinite fields in string theory, the only ones that survive are the dilaton. So the string coupling, so theta of X is, so the different X's correspond to disjoint universes. X is an entire universe. It's just a point, zero-dimensional string theory. And the only string field that really remains is the dilaton, whose value on the universe X is the string coupling. So theta X is G string to the -2 on that universe. Okay, now let's look at the amplitudes. So everybody knows that the vacuum-to-vacuum amplitude in string theory is the sum over the amplitudes on the connected Riemann surfaces of genus 0, like Y0, Y1, and Y2, and so on. And so that sums up nicely to the trace on 1 over 1 minus H, where H is the handle adding element defined by the one-hole torus with one outgoing circle. And so in the semi-simple case, that becomes a sum over the universes of lambda x, where lambda x is just the geometric sum of the string coupling. Okay, so it's expressed in terms of the data of the Frobenius algebra very simply like that. Now, the fun starts when we start to look at non-zero boundaries, non-empty boundaries. So let's warm up to it by thinking about two disjoint union of two circles going to nothing. And for simplicity, again, I'm going to take my Frobenius algebra to be one-dimensional. So phi 1 and phi 2 are proportional to the idempotent epsilon. And so now let's first think about what kind of bordisms are there from two circles to nothing. Well, first look at the case where there's one connected component. So they have to look like this. We can have an annulus with two ingoing circles, or we can attach any number of handles to it. And so when we attach handles, we're just making a geometric sum with the string coupling. And so phi 1, phi 2 goes to Z1, Z2 lambda. So that's what these bordisms give. And similarly, if I have one connected component and n ingoing circles, I just multiply up the z's and I have a single geometric sum over the string coupling lambda. Okay, now let's return to the case of just two circles. So in addition to one connected component, I can have two connected components. And then I can attach any number of handles to each of those connected components. So altogether, phi 1 tensor phi 2 maps to Z1, Z2 lambda squared. So altogether, the amplitude, the total amplitude from two ingoing circles to nothing is Z1, Z2 e to the lambda, because of course I can just include all those disjoint closed Riemann surfaces, the vacuum to vacuum amplitudes in my bordism. And then we have lambda plus lambda squared. And Maroff and Maxfield recognized lambda plus lambda squared as what's known as the second Bell polynomial. Okay, so I had to look it up. What are Bell polynomials? So the nth Bell polynomial is a polynomial in variables x1 to xn, which counts the number of ways a set of n elements can be partitioned in such a way that the coefficient of, say, x1 to the k1, x2 to the k2, and so on, counts the number of disjoint decompositions where there are k1 subsets of cardinality 1, k2 subsets of cardinality 2, and so on and so forth. Now, what's going to be relevant to us is the nth Bell polynomial where all of the x's are set equal to lambda. And why is that? Well, now think for a second about, think about what kind of bordisms are there from n disjoint circles to the empty set? Well, if you have such a bordism from n disjoint circles to the empty set, you could divide it into its connected components. And some of those connected components are going to have j ingoing circles, where j runs from 1 to n. And how many connected components will there be with j ingoing circles? There'll be, say, kj. And then to each of those connected components, we can attach handles as many times as we like. And so that describes for you your general bordism. Now, as I remarked, when you have j ingoing circles for any j, and you're summing over all the connected bordisms to nothing, then you get a factor of lambda. So the upshot is that the Hartle-Hawking covector is just the sum of the nth Bell polynomial on the diagonal times the dual of our idempotent to the nth. The dual because we've got n ingoing circles mapping to nothing. All right, now applying the dualization, the U-shaped morphism to get ingoing and outgoing circles, it's the work of a moment to get the general summed amplitude, the total amplitude, in fact. So Ni is the number of ingoing circles, and out is the number of outgoing circles. Now there's a nice identity for the nth Bell polynomial that looks like this. E to the lambda Bn of lambda is the sum from d equals 0 to infinity of lambda to the d over d factorial d to the n. This was used extensively in the Merrill-Maxfield paper, and I will shed some light on this identity in a couple of slides down the line. But for the moment, just accept this identity. So here's our total amplitude, and now here's our identity. So just plug it in, and you get, obviously, that equation. And now you start to see the splitting, because you see we can bring things that depend on Ni ingoing circles to the left and outgoing circles to the right. And we think of D as sort of parametrizing intermediate states. So to give that mathematical precision, we note that the Frobenius structure gives us a canonical sesquilinear form such that epsilon dagger is theta times epsilon dual. And now our splitting space will just be the same Fock space of C that we have for our gravity theory. And then what you find is that if theta is real, but not necessarily positive, indeed the amplitude splits as phi dagger, where here's the explicit formula for phi. So if you imagine taking this phi and then taking its adjoint and contracting the terms that involve d's, then you're going to get the amplitude I showed before. All right, I'd like to make a few comments now about these quantum gravity amplitudes. First of all, the amplitudes can be invariant under the action of a non-trivial global symmetry group. So for 1 dimensions, it would be the orthogonal group of the bilinear form. And for 2 dimensions, well, you know, these Frobenius algebras can have automorphisms. If I have a bunch of universes with the same string coupling, then I can have the symmetric group acting as a group of global symmetries permuting the universes. So in general, I would have some product of symmetric groups as global symmetries of my Frobenius algebra, and of course our amplitudes are invariant under that. So, you know, people like to go around saying that you could never have global symmetries in quantum gravity. And I guess the lesson that we learn from this is that, well, you need to have slightly less baby versions of quantum gravity for that to be true. Similarly, the amplitudes can depend on continuous parameters manifestly. Something that caught me by surprise is, you know, we have this Hartle-Hawking vector, which is the sum of nothing goes to something, and the Hartle-Hawking covector, which is the sum of something goes to nothing. So you might think that the contraction of the Hartle-Hawking vector and covector is the vacuum to vacuum amplitude, and that's far from the case. The vacuum to vacuum amplitude is finite. The contraction of the Hartle-Hawking vector and covector is in fact divergent. I found that surprising. And now perhaps most importantly, there's a close relation here to coherent states, which was also very important in the Merrill-Maxfield paper. So I'm going to explain this 4th point in more detail now. What do I mean by coherent states? Well, let's take a bosonic harmonic oscillator, namely a Heisenberg algebra. The commutator of A dagger is 1, A is bosonic. And so, of course, it has a canonical highest weight representation, or lowest rate representation, depends on your point of view. And we can form an orthonormal basis for that representation by taking a dagger to the d over the square root of d factorial, call that kept vector d. And in terms of the sesquilinear structure I mentioned before on the symmetric algebra, it corresponds to the idempotent epsilon over the square root of theta to the d. Okay, so by definition, a coherent state is a state in the Hilbert space of the harmonic oscillator, which looks like this. So we have an exponential of some factor times a dagger acting on the vacuum. Now, the coherent state has a nice property. If I introduce the number operator, a dagger a, and consider the expectation value in a coherent state of the small nth power of the number operator, then you could show that's e to the lambda bn of lambda, where bn is this Bell polynomial. And now if you expand this in the D basis, you get the identity I mentioned before. So that's very interesting, because that gives us an interesting point of view on these total amplitudes. So let's introduce what you might call the universe annihilation operator. So it takes our splitting space W and it maps it to C dual. C is our Frobenius algebra for quantum gravity. C dual tensor W. And here's the explicit formula for this map in a basis. And the universe creation operator goes from W dual to W dual tensor C, and it's explicitly given by this. And then the total amplitude that I wrote before could be written as this inner product. So as you know, so you see, you contract out the blue stuff, the stuff having to do with the splitting space, and you get an operator on the Fock space of the Frobenius algebra, C. All right, so I think that's a pretty interesting formula. Let me explain why. So Maroff and Maxfield's paper supports the whole purpose of their paper is to support this point of view that, well, ADS-CFT is really about ensembles of quantum field theories being dual to quantum gravity. But there's another point of view, which this formula suggests, which is that in some sense, the splitting space is the Hilbert space of a dual quantum mechanical system to the quantum gravity theory. So this is a more abstract version of holography than what we're used to, because the splitting space W is not associated to any particular region of space-time. I mean, what region of space-time? We're summing over all bordisms. There's no special region of space-time. But nevertheless, there is some Hilbert space out there, and we can do calculations in that Hilbert space, which is what you do in quantum mechanics, and produce amplitudes of quantum gravity. So again, you see this is what I mean. We trace out the blue stuff, the splitting space stuff, and we get an operator on the Fock space of the Frobenius algebra. And another reason I like this point of view is that it's reminiscent of something I like to call quantum mechanics with non-commutative amplitudes. So, you know, in standard quantum mechanics, we have wave functions, some vector in a Hilbert space, and probability amplitudes are expressed in terms of overlaps. And typically, you know, and our overlaps, we have a sesquilinear form valued in the complex numbers. So something I once thought about is, well, what if we had quantum mechanics with non-commutative amplitudes where the overlaps were valued in a non-commutative C-star algebra? So then if you follow through that idea, then the psi's are valued in a Hilbert C-star module. And how in the world would you write a Born rule for that? Well, I gave an answer a few years ago. And one of the things that I find interesting is that, a shortcoming of my paper from 2017 is that I didn't really have a killer app for this idea. I was just thinking about this potential generalization of quantum mechanics for its own sake, and I had some applications, but nothing terribly convincing. So here, you know, it's just being handed to you by the following your nose in this theory that you're getting inner products valued in operators on some Hilbert space. All right, so now let's come to the open and closed case. Let's see, I started it. Okay, I'm doing okay, I think. Let's come discuss the open and closed generalization. So I'm going to talk about open and closed two-dimensional TQFT. It's going to be oriented and semi-simple. So now the in and outgoing manifolds are going to be disjoint unions of circles and oriented intervals. We could think of the intervals as one morphisms in a category of manifolds with corners. So they are going to be intervals like this. And the functor is going to assign to the endpoints of those intervals objects in a category of boundary conditions in such a way that the value of the functor on such a labeled interval is the Hom space in the category, or in physics, that's called the open string space with boundary conditions A and B. So now the surfaces are two morphisms in a two category. Here's a typical two morphism. So there might be some ingoing boundaries on the left there in red, and an outgoing boundary on the right in purple, a purple interval. And now you see the endpoints of the intervals have to get connected, and they're labeled by a boundary condition. So now we have three different conceptual kinds of boundaries. In our bordisms, we have the ingoing and the outgoing, and what Graham and I call the constrained boundaries. We can also have closed constrained boundaries. That's really modifying our bordism category a little bit. So really, there are three conceptually different kinds of boundaries. You can have in and outgoing circles and intervals. You can have the constrained boundaries connecting in and outgoing endpoints to in and or outgoing intervals. And you can have closed constrained boundaries. And there were a bunch of puzzles. One of the reasons I'm mentioning is that there were a bunch of puzzles in the Merrill-Maxfield paper. And I think you can trace a lot of those confusions back to the fact that they were not really careful about the distinctions between these conceptually different kinds of boundaries. But I'm talking to the mathematicians, so let's not go there. So let's look at the splitting formula in the simplest case. And for simplicity, we can relax, and we do in our paper. We relax all these conditions in our paper, but just for simplicity of presentation, let's take the Frobenius algebra to be one-dimensional. Let's take all the constrained boundaries to be labeled with a single boundary condition. I'll call it A. So Hom AA is in fact an algebra OAA. And let's have no closed constrained boundaries, and all of the in and outgoing manifolds will just be intervals. So no in or outgoing closed strings. So to write the amplitudes, you actually have to take a square root of the trace of the closed string Frobenius algebra. Physically, that mu inverse is the open string coupling. And what we find is that for splitting, we need to have mu real, so theta is greater than 0. Then we do have the splitting. And now phi is naturally written as a map from the symmetric algebra of the open string algebra, OAA, to an L2 space of a space of n by n Hermitian matrices. So I need to explain a little bit here. So there's something in two-dimensional open closed topological field theory called the Carty condition, which implies that this open string algebra OAA is not just any old C-star algebra, but it's just a finite dimensional full matrix algebra. So there's an integer there, NA, and the E sub NA is the vector space of NA by NA Hermitian matrices. And so here's an explicit formula for the splitting. So in this part of the formula, I'm just basically summing over, taking into account the sum over all possible ingoing states. So the sum over little n is the sum over n ingoing intervals. And then I sum over pairs, I1, J1, I2, J2. And then EIJ is a basis of matrix units for this matrix algebra. So EIJ dual is the dual basis. And then the interesting part is that we're mapping to this L2 space of the Hermitian matrices. So on the far right, you see the bra vector of H. H is a n by n Hermitian matrix. And we have a matrix model. And the potential for the matrix model is given by this formula. It's a Laplace transform of the exponential of lambda. Lambda, remember, was the geometric sum of the closed string coupling of 1 over the determinant of 1 minus s to the open string coupling. A corollary of this is that the Hartle-Hawking covector evaluated on e to the t is given by this very simpler formula, which appeared in, without really saying what they were computing, but my interpretation of what they were computing is they were computing the Hartle-Hawking covector. That formula appeared in a follow-up paper to Maroff and Maxfield by Gardner and Megas. Okay, so I've said all this before in a few talks. I have a few minutes. So one thing we've done since then is we've worked out a little bit about the coupling to two-dimensional Yang-Mills theory, which is interesting because it's no longer exactly topological. So let's consider two-dimensional Yang-Mills theory with a compact connected simple Lie group G. So now our morphisms are surfaces with a total area A, which is considered to be additive under gluing. And so the space of states now associated to a circle is a tensor product of our original Frobenius algebra for the quantum gravity with the L2 class functions on the group G. And so we have a nice orthonormal basis here given by the characters where R runs over the unitary dual of G, the irreducible representations of G. And so let's just look at the vacuum amplitude. So, famously, going back to famous work of Sasha Migdal, the partition function of 2D Yang-Mills theory on a fixed Riemann surface of genus G would be the sum over all the irreducible representations of the dimension of the representation to the Euler character times e to the minus a, the area measured in units of the coupling constant, times the quadratic Casimir of the representation. So now when we couple with quantum gravity, we include this trace theta, again, to the Euler character, or rather 1 minus g. And it turns out it's really important to include a cosmological constant, which is positive for things to exist, for amplitudes to exist. So it's not quite topological gravity, but it's almost topological gravity. It's topological gravity for surfaces endowed with a total area. Now, in the sum over bordisms, I have to sum over the genus, and I also have to integrate over this area. And I integrate with a measure dA over A times A to the P. And P, I'm just putting in here for convergence reasons. And I imagine that the nature of P depends on particular nature of the quantum gravity we're coupling to, but that's a point that really needs to be understood much better. Anyway, if you grant me that I can put in this convergence factor P, then it's work of a moment to sum over the genus and integrate over the area. And so what we get is the sum over the unitary dual of lambda r, where lambda r is this mess. And now you see we have theta times the dimension of r squared in the numerator, and the quadratic Casimir in the denominator. So we better take the real part of P to be bigger than the number of positive roots plus a half for convergence. But then we will have convergence, and I expect that this admits an analytic continuation in P. So this is some funny generalization of the Riemann zeta function. And I expect it has an analytic continuation in P. And so if we need to put P equal to various values for various quantum gravity theories, we can analytically continue and hope that we're not sitting on a pole. That remains to be seen. You can also evaluate, we have evaluated the Hartle-Hawking covector, and it leads to this rather on the exponentiated diagonal, which, as I explained before, encodes the entire Hartle-Hawking covector because it's symmetric and multilinear. And so it leads to this rather curious formula with a product over the irreducible representations of something very simple. And if you think about what I said before, that strongly suggests that there's going to be, again, factorization. And again, in this case, the splitting space is going to be the Fock space on the space of states associated with a single circle. So it's very much like the closed string semisimple case. Okay, so let me say a few words about 3 dimensions and higher, the last few minutes. It will be really fun to extend these ideas to 3-dimensional TQFT and higher. But to put it mildly, the classification of manifolds is much more difficult. So even the trivial part of our story really is the vacuum to vacuum amplitude. And what do we have to deal with now? Well, we have to sum over all closed connected three manifolds weighted by the topological quantum field theory partition function for that three manifold. Well, wait a moment. I mean, that sum includes the sum over things like S1 times a Riemann surface of genus G. But then Z of Y is just the dimension of the space of states, genus G. And for the standard fully local TQFTs like Chern-Simons-Witten theory that we know and love, well, that dimension of the space of states grows with G. And so our sum is really irretrievably divergent. So I was thinking for a while that, well, okay, maybe I could have a interesting TQFT where the dimension of the space of states is 0 for sufficiently large G. Can you have a three-dimensional topological field theory where the space of states just somehow starts becoming 0 for sufficiently topologically complicated Riemann surfaces? And after talking to Sergei Gukov, I realized the answer is no. He pointed out to me, well, look, you could cut along the boundary of a handle body surrounding a small handle body surrounding any point in any three ball. And because of that, you have a curious fact that if in a 3D TQFT, if the dimension is 0 for any genus, then all the amplitudes in the 3D TQFT vanish. So no, that possibility is shut off. So we're kind of at a loss here about what to do about three dimensions. And it's like an inconvenient truth that a lot of people who work on 3D gravity seem to just ignore. Maybe there's some way to modify the domain or the codomain categories to produce interesting examples. I don't know. I haven't been able to get anybody with great expertise in N categories to help me explore that possibility. One in this dark night here, there's one possible gleam of hope, but it's very, very faint and very, very tentative. It comes from discussions with Sheryar Sikander. He keeps reminding me of an amazing and very deep theorem, the virtual fibering theorem, which says that a closed connected hyperbolic threefold has a finite cover by a pseudo-Anosov mapping torus. So our hope is that maybe you could sum over pseudo-Anosov mapping tori and then bound the sum by using some version of a Selberg or Gutzwiller trace formula. And whether that leads to anything at all, I really can't tell you at all. So it's just a proto idea in the very beginning stages. So let me summarize. I think I'm out of time, almost out of time. Yep. What did I say? So for suitable parameters of our TQFT, the total amplitude, which is a linear transformation on the symmetric algebra on the state space for all connected manifolds, the Fock space of Z, it has a splitting. A bar is phi dagger, where phi is some map from the Fock space of Z into inner product space W, the splitting space. And we worked out some examples. I didn't show you, but in India, and I also worked out some examples for non-semi-simple two-dimensional TQFTs. And it's not trivial from the formulas, but we checked that a splitting still does persist. Now we're really doing this example by example. So there are lots of extensions that we didn't check, like the general non-semi-simple case, other tangential structures like unorientable, spin, pin, and so on. We are looking a little bit into the G equivariant theories for a finite group G. That's interesting because then it's natural to include in the TQFT B fields. So something I'm curious about is whether we can have a splitting for a general B field or whether the existence of a splitting constrains the B field. I really have no idea at all at this moment what's going to happen. And as Kevin was pointing out to me, we really ought to think about these kinds of questions for topological string theory. where we're going to talk about some kind of linear transformation on a Fock space built on the quantum cohomology of a Calabi-Yau manifold. Now, something I worry about is that maybe I've just wasted an hour of your time. Maybe the existence of a splitting formula is just a trivial consequence of linear algebra. And what's the rough idea for that? Well, the total amplitude has got to be symmetric under the exchange of ingoing boundaries for outgoing boundaries. There's if we don't put any orientation, and there's no distinction of in and out. It's just an arbitrary disjoint decomposition of the boundaries. So everything has to be symmetric under exchange of in and out boundaries. But at least in finite dimensional complex matrix world, any symmetric matrix can be written as phi transpose. Now, I haven't been able to take that kind of argument and make it a convincing argument for the existence of the splitting in our cases, but it does make me worry. If it isn't just a consequence of linear algebra, then we need something more intelligent than a case-by-case check, which is what Anandi and I have done. We've just been doing case-by-case checks to see, well, is there a splitting? Can we find a W and a phi? Is there some a priori reason why such a splitting should hold? I should remark that because of this great debate about whether ADS-CFT involves ensemble averages in it of quantum field theories or not, a splitting formula for JT gravity could have interesting implications for that debate. And to my mind, the most pressing question here is what to do about 3 dimensions and higher. And so with that, I thank you for your attention. And once again, I thank Sasha for lots of great conversations, and I wish him happy birthday.
Thank you, Greg.
Thank you.
Oops.
And we have time for some questions.
Can I ask a question again?
Yes, please.
I'm still confused by the symmetry factor.
Yeah.
Because you would think it should involve the mapping class group at least, which is
Yeah,
infinite.
that's pretty much what Maxime said.
How do they justify this?
Some remarkable conjecture about the B diff relative to the boundary, if I can remember, of manifolds being, I think he wants to say it's like a finite CW complex. Anyway, he has a conjecture of that nature, and I'm not quoting it correctly, but in fact, it was proven many years later by some topologists. So yeah, I mean, just all I'm doing, Kevin, is what people do in topological string theory when they exponentiate the amplitude, the vacuum to vacuum amplitude. What do? We exponentiate. We sum over connected Riemann surfaces, right? So that's all I'm saying.
But I feel like there you've already taken care of the 1 over mapping class group is captured by the integral over moduli space.
Well, that's true. That's true. Well, okay. So yes, I mean, when you derive the Polyakov path integral from the path integral, what do you start with? You start with the integration over all metrics on a Riemann surface, and then you divide by the volume of the diffeomorphism group, which physicists sort of make sense of. Well, actually, it's the volume of the diffeomorphism group times the group of Weyl rescalings. And what you get is a finite, well-defined measure on moduli space. So yeah, I'm with you there. You certainly do divide by that. The volume, the diffeomorphism group volume.
But why do the quantum gravity?
Because we're here we're talking about the purely topological case. So the amplitudes don't depend on the metric. So I mean, one aspect of this, which I find kind of weird, is that, if you have, as I said, if you have, in the two-dimensional case, imagine you have a bordism from some number of ingoing circles to some number of outgoing circles. And then you have, disconnected, N0 disconnected spheres and N1 disconnected tori and so on. And then you would divide by 1 over N0 factorial, 1 over N1 factorial. But if you have a bunch of, just cylinders from an ingoing circle to an outgoing circle, and you have N of them, you don't divide by N factorial. That's why I said the diffeomorphism has to restrict to the identity on the boundary. So you're not allowed to permute those tubes. And I did play around with changing that rule, and you get different results. But I stuck to the rule I used because that's what people do. And certainly, there's something good about it because it leads to this non-trivial stuff with Bell polynomials and coherent states. And so, that was not put in at all. That comes out, and that comes out with this way of dealing with the combinatorics. But yeah, something I'd like to do is think a little more carefully about Maxim's objection and maybe try and find some good alternatives to this general idea of summing over bordisms. I guess I should say Maxim's objection and your objection, because you came up, you instantly jumped on exactly the same thing that he did.
Well, I think anybody who's thought about topological strings will.
Oh, well, okay. Well, you guys had the first opportunity, so to object.
Other questions for Greg? I wanted to ask, so you were describing a construction which you could do, or you could try to do anyway, with any topological field theory, and you were comparing it to this paper of Morolf and Maxfield. Right. In that paper, did they use some particular TFT?
Well, they don't even say it that way.
Can you interpret their constructions as
yes.
Which one?
Yes. Yes, they don't even say it that way. What they were doing is, let's see, actually, let me share slides. Am I still sharing slides?
Yes.
I brought up the gallery of people so I could talk to them. Okay, I am still sharing slides. Okay, good. Okay, let's skip all this. I think I put in one of my supplementary. Yeah, I figured people would be less interested in. No, damn. Here we go. No, I didn't include the relevant. Okay. Well, you see, what Maroff and Maxfield were doing, is just considering. Yeah, I deleted the relevant slide to answer your question, Andy. It's in another talk. What Maroff and Maxfield, I have a slide explaining the answer to your question, but what Maroff and Maxfield were essentially doing was taking a Frobenius algebra, which was one-dimensional.
Okay.
And what they said is, let's take gravity. Okay. This is what they said. They said, let's make a model of topological gravity where the action is the Einstein-Hilbert action. So it's just the Euler character. And there's a parameter in front of that. They called it S0 because it's related to some, in their world, it's an entropy of a black hole or something like that. Plus another parameter they called S boundary times the number of components of the boundary. And they said, let's sum over all surfaces with boundary weighted by the Euler character, e to the S0 times the Euler character, times e to the S boundary times the number of boundaries. And a number of people immediately said, well, look, the number of boundaries is not an integral of a local density. Okay, so that's an example of the kind of paradoxes or puzzles that were raised by their work. And if you follow through, what I said about the conceptually different kinds of boundaries in open closed string theory, a 2D open-closed string theory, then you see that's a non-worry. They just were confusing a term in an action with something, a fugacity. But that's their model. That's their model. So in our language, it's just coupling to the simplest possible closed 2D topological quantum field theory, namely a one-dimensional Frobenius algebra, and the Einstein-Hilbert action is given by the trace on the idempotent.
Great, thanks.
I mean, the real insight was, let's consider, in and outgoing circles and take seriously the sum over all bordisms, connected or not. I'd summed over bordisms myself in the past. And, when I teach courses on this kind of stuff, I always point out that you could easily sum over the genus. But, but there's this really interesting structure having to do with coherent states when you think about the combinatorics of connecting the ingoing, possible ingoing boundaries to outgoing boundaries, allowing for disconnected bordisms between in and out. For me, that was the real insight from their paper.
Thanks. Any other question?
Yeah, so I have a question, in fact.
Yeah.
Do people study this kind of topological quantum fields with coefficients in different fields other than other than complex numbers?
Yeah, that's an interesting question. I tried to do as much as I could over a general ground field. But then I got lazy when it came to the splitting, and because I just wanted to write down a simple sesquilinear form, so I assumed that the ground field was C. But I suspect you could do a lot over a general field, but I didn't really explore that too much. So yeah, in my paper with India, I kept the ground field general as long as I could, and until I got lazy, and then made it C.
Cool. Yeah, thank you.
All right. Well, let's thank the speaker again.
Okay. Well, thanks to the organizers. I've only been present for a few of the talks, but it was really a very nice conference. Happy birthday, Sasha.
Thank you. And I would like to thank all speakers today for the wonderful talks, and all organizers again for making all this possible in spite of COVID and other things. So thank you very much.
Let's thank everybody then.
And I imagine with this, the conference is finally over.
Okay. Bye-bye.
Bye.